Okay, so we need to talk about a new kind of AI chip coming out of China, because this one is, well, it's radically different. It doesn't use electricity to think. Nope, it uses light. And the performance numbers are already making everyone sit up and pay attention. Right out of the gate, we're talking about a theoretical peak performance of 2,560 tops. That's trillions of operations per second. Now, to give you some context, that puts it right up there in the same league as some of the most powerful GPUs you can get today.
So the question is, how on earth is that even possible? How are they getting that kind of horsepower from a chip that literally runs on beams of light instead of streams of electrons? Let's dive in and break down the tech behind this.
All right, the star of the show here is a chip called the Meteor 1. It's an optical AI accelerator, and it was developed by the Shanghai Institute of Optics and Fine Mechanics. This little thing is the heart of the entire breakthrough.
The secret sauce that makes the Meteor 1 work is a technique called wavelength division multiplexing. It sounds complicated, but the idea is actually pretty genius. Instead of sending just one signal at a time, the chip takes a single laser, splits it into 100 different colors, or wavelengths, and sends a totally separate stream of data down each and every color, all at the exact same time.
The best way to picture this is to think of it like the ultimate data highway system. You're not just adding another lane to the road. You're instantly creating 100 brand new, completely clear highways right next to each other, allowing for an absolutely massive amount of data to flow through. That parallelism is what makes this so powerful.
And that brings us to the really fundamental question. Why even bother with light? Well, it's because our good old traditional silicon chips are starting to bump up against a wall, a physical limit to how much faster we can make them. Photonics, or using light, is a way to just sidestep those limits entirely. The difference is really night and day. When electrons move through silicon, they create resistance, and that resistance creates heat. It's that heat that becomes the bottleneck, limiting how fast and how dense you can pack your circuits. But light? Light just zips through optical materials with almost zero resistance. That means way less heat and much, much lower power consumption to get the same job done.
So let's just sum it up. You get rid of the heat problem, you open the door to basically infinite bandwidth, you get massive parallelism baked right into the physics of the thing, and you do it all while sipping power. For AI workloads, this is basically a cheat code. So much of what AI does, like training large language models, just comes down to doing tons and tons of matrix multiplications. And those calculations are perfect for being done in parallel, which maps perfectly to those 100 light-based highways we were just talking about.
Now, you've probably seen headlines that scream things like this. It's really easy to hear photonic and have your brain immediately jump to quantum computing. But we need to be super clear about what this technology is and what it isn't, at least not yet.
Let's pump the brakes for a second. These are not quantum computers. They don't use qubits or quantum entanglement. They are what we call classical optical accelerators. They use the properties of light for regular computation, just on a massive scale. But, and this is a big but, the architecture they're building absolutely lays the groundwork for future hybrid systems. So think of it as a really critical stepping stone on the path towards quantum, but it's not the final destination itself. You know, having a single breakthrough chip in a lab is one thing, but being able to actually manufacture it at scale, that's what really changes the game. And this is where we see China's strategy coming into focus, moving this tech from a prototype toward mass production. In June of 2025, China flipped the switch on its very first pilot production line for something called thin-film lithium niobate wafers, or TFLN. That's the super specialized, transparent material these optical chips are actually made of. It's known for being incredibly efficient at handling light. Building a domestic factory for this stuff is a huge step towards self-reliance in this new field. And the scale here is pretty significant. This first line is designed to churn out 12,000 of these wafers a year. That number tells you this is a serious commitment. This isn't just a research project anymore. It's about getting this technology into the real world. So you have to ask, why the massive push right now? Well, there's a pretty clear geopolitical context here. With ongoing export controls on advanced silicon GPUs, China is strategically pursuing photonics as a completely different path forward. It's a way to sidestep existing restrictions, build up domestic expertise, and maybe, just maybe, leapfrog ahead in the next great computing race. Look, this isn't just about one chip or one factory. What we're seeing here is the unofficial starting pistol for a whole new race in computing.
one where the fundamental building blocks might not be electrons, but photons. And the implications of that shift are absolutely huge.
So, the natural question for all of us is, what does this actually mean for us? Where are we going to see the impact of these light-powered chips first? The list of potential applications is just massive. We're talking about everything from incredibly efficient AI data centers to the backbone of 5G and 6G networks, faster and smarter autonomous driving systems, aerospace, advanced medical imaging, even high-frequency financial trading. Basically, any industry that is starving for more bandwidth and less power consumption is a perfect candidate.
And here's the bottom line. If this technology can scale successfully, and that is still a big if, the fallout could be enormous. We're talking about a potential disruption to the entire silicon-based GPU industry. The kind of dominance that companies like Nvidia have built over decades could face a really fundamental challenge from a completely new way of computing. So the real takeaway here is that while silicon isn't disappearing tomorrow, the ground beneath the future of high-performance computing might be shifting. We are watching the very early days of a new technological race, one that could totally redefine what's possible in the world of AI. The future is changing, and it looks like it might be a whole lot brighter.